When we learn about arrays, we're always told one thing. Arrays are contiguous blocks of memory. But here's the catch. That's not the whole truth. At the programming language level, especially in C or C++, an array does appear contiguous. If array starts at address 1000 and each element is 4 bytes, then index 1 is at 1004, index 2 is at 1008, and so on. You can verify this yourself with a simple C program that prints the addresses of an array. To understand the full picture, we need to dive into how memory works in modern computers. I want to get it into step by step. Let's rewind a bit. Imagine the early days of computing, when only one program could run at a time. This was called monoprogramming. The entire program was loaded into a single, contiguous block of physical memory. No overlaps, no sharing. When it finished, the next one loaded in. No problem. This is not the case in modern computer. More than one program can run at a time, meaning multiple programs can be stored in a memory. Let's see what happens if we use contiguous memory allocation in multiprogramming. Consider you have 1 gigabyte of memory and 124 megabytes is already occupied by the operating system. You have remaining 900 megabytes of memory. You want to run 3 programs and each program takes some amount of memory. Let's say programs take the following amount of memory. At first, VS Code and Firefox fit just fine. But when Chrome arrives, only 200 megabytes is free, not enough for its 500 megabytes request. Later, when VS Code finishes, another 200 megabytes gets freed, making the total free space 500 megabytes. So, can Chrome run now? Unfortunately, no. Why? Because that free memory is scattered, not continuous. This issue is called external fragmentation. You might think, why not split Chrome across the holes? It's possible, but managing it manually is inefficient and error-prone. Plus, programs expect contiguous access for things like arrays. Another big issue, security risks in shared physical memory. In contiguous allocation without protection, all programs share the same physical address space. A buggy or malicious program could read or write to another's memory. The key problem here is that each program is accessing same memory space. If we could give each process its own memory space, we might be able to solve these problems. Operating systems do so. It gives each process its own virtual memory space. It's like each program lives in its own private universe of addresses, starting from 0, isolated from others. But virtual addresses aren't real. They need mapping to physical RAM. This is where paging comes in. Virtual memory is divided into fixed-size chunks called pages, typically 4 kilobytes. Physical RAM is divided into matching chunks called frames. The operating system maintains a page table for each process, mapping virtual pages to physical frames. For example, if physical RAM is 100 megabytes and frames are 4 kilobytes, number of frames equals 25,600 frames. Let's assume each process has a virtual address space of 16 megabytes. So virtual pages per process equals 4,096 pages. Now the OS maps these virtual pages to physical frames via a page table. These mappings may or may not be contiguous. OS finds the currently not using frames and assigns them to pages. But how does the CPU actually translate a virtual address into a physical address during execution? Let's break it down. In a 32-bit computer, each process has a maximum of 4 GB virtual address space. With a 4 KB page size, the virtual address is divided into 2 parts: virtual page number, 20 bits, and page offset, 12 bits. The CPU uses virtual page number to index into the page table for the current process, and the page table tells us which physical frame number this virtual page is mapped to. While page offset is unchanged, it is combined with the physical frame number, and the result is read memory address. For translation, special hardware is used, Memory Management Unit, or MMU. Now coming back to arrays, in your C or C++ code, array at index I is calculated as base address plus I times size of element. This arithmetic assumes contiguity in virtual addresses, which is always true. The OS and hardware handle the non-contiguous physical mapping behind the scenes, but in physical RAM, nope. Those pages could be scattered across frames due to paging.